Okay. So we have just started the recording. So we are now being recorded. So let's take a look. So the last check, Radek,
Yes.
can you hear me? Can you see me?
Yes, I can both see you and hear you, so
That's
everything
great.
seems to be okay.
Okay, that's great. So it's 2 p.m. So we are definitely, it's time. So we are about to start. So as usual, let's give it a couple of seconds or dozens of seconds, and then we will really go for it for hard. So what else? The presentation is here. Let's make it happen.
Yeah.
People are coming. I can see a lot of them already. Okay, that's great to see you. Yes. Hello. Yeah. So let me close this window and that window and minimize this.
Yeah. Do not close the webinar window, please.
Yes. That's the last one I will keep on. And I think maybe it's time to start, right?
Go ahead.
Okay, so let's do it. So maybe we will cut it here or not. Let's see. Maybe we will be lazy tomorrow. So, but let's start the webinar. Okay. Yeah. So I'll start it. I'm starting it actually right now. So hello everyone. This is Luboš Pirkl from CFD Support. I would like to welcome you to the webinar, which is called Centrifugal Fan, CFD, FEA, FSI, and Optimization. It's webinar number 79, and we'll be happy to show you what we have here, what we have done recently, what changed, if anything, in our old good workflow of centrifugal fans simulation. So yeah, we started a little bit earlier, 1 hour earlier for today, because we simply want to make our webinars a little bit longer. We want to go home at the same time as we usually go, so we we started a little bit earlier. That's the real reason, and we want to be more informative. We want to show more detailed things. We hope it's a benefit. So I will explain a little bit more during my presentation why we are doing this, and yeah, so welcome, and we will do our best to show what we have. So the webinar is being recorded. The recording will be later made publicly available on our YouTube channel. So yes, the recording will be available. If you miss anything, you can still see it on your leisure time. There will be a couple of parts. In the first part, again, I will show what's new, what we have, what is the software, what's the company, general information basically. And in the largest part, the technical part, my colleague Radek will show you how to do things. We will show pretty extensive information about the workflow, how we really do things, how centrifugal fans or general turbomachinery can be simulated. And there will be also the Q&A session, and the last part will be dedicated to your questions and our answers. So feel free to ask your questions, and we'll be happy answer them. All the questions will be answered, of course, as usual. So we will answer the most relevant and representative questions right in the webinar. The rest specific questions will be answered later via email, but you can be sure that all the questions will be answered. So feel free to ask your questions. There's a window in the GoToWebinar menu. So feel free to ask your questions anytime during the webinar before you forget them. So ask about them, and we'll be happy to answer them. Yes, yeah. So hopefully we set something, and let's go ahead. So this is me. I'll take the general part. Together with me on the line is my colleague Radek Máca, who is our colleague and engineer, and let's check if he can see us and hear us. So Radek, so are you There?
Yeah, I am. I can see, I can hear, and welcome the audience to the webinar. So I think everything is set and ready to go.
Great, thank you, Radek. Yes. So okay, so I'll start the general information, and we will get through it over the time.
Yeah.
So yeah, let's go ahead. So this is, yeah, today's webinar is about centrifugal fan. Yeah, it's important to say that it's especially dedicated to the CFD and FEA part. It's not much about optimization, because there will be other webinars about specifically dedicated to the optimization. So if we say not much information, or not as much information as you could expect, definitely for example, the next webinar is specifically dedicated to optimization of turbomachinery components. So yeah, there are scheduled quite a few next webinars for the remaining rest of the year with different topics. So feel free to, yeah, of course, attend the next webinars. So there will be, I will quickly go through them. So the next webinar will be about the optimization of turbomachinery components. Another webinar will be dedicated to new acoustic benchmark, axial fan, which yeah, deals with acoustic simulations. There will be webinar on Kaplan turbine, and also the next webinar will be on remote computing using our software. So there are a lot of options you can use, how to use the software, which is extremely flexible in these terms. There will be webinar on centrifugal pump and pumps in general. Another webinar about external aerodynamics, specifics about external fluid flows, centrifugal compressor, Francis turbine, and also noise reduction techniques webinar, and wind turbine webinar, and also blood pump webinar. So those are a couple of webinars we have scheduled for this year, and perhaps there will be more content we will add over the time, like new versions and etc. Yeah, which makes me think maybe we will switch the cameras off for now, right? And not to disturb the audience with our faces, and we will get back for the Q&A. Hopefully we will not forget.
Yeah, sure.
Okay, so I'm switching my camera off at the moment. So
okay.
bye now, and you will definitely hear just the voice and see the presentation. So yeah, so quickly I'll go through the general information, because typically for the webinars there are the majority of the audience is newcomers, new people. So we will definitely, we have to say what's on the table, what's what. So okay, I'm starting with the information. I guess you know that the CFD Support is the company name. So our company is called CFD Support. We are like 15 years in the market, and we deal generally with simulation for the industry. Especially we deal with CFD. That's after all, it's in the name of the company, and with FEA simulations, FSI, optimization, and acoustics. So those are, I would say, our the most important fields we deal with, but it's definitely engineering simulations. We do quite a lot of consultancy, but the main thing we offer here, we bring here is the simulation environment, which is our flagship product. It's called TCAE, and it's a software, a code which we developed over those years, and we have put in it all our passion, experience, skills, knowledge, and all the effort has been put into this, and also a lot of experience from real projects which we did in hundreds over those 15 years, and all that has been put into software which we are using in projects, and we are developing it, maintaining it, and selling it. So it's TCAE, so we call it comprehensive simulation environment, and it's a software which is based on open source, and it's been developed to deliver as much value for the users as possible. As we are growing older and getting more smarter and wise, we realize that it's not just the software what we are selling here, right? It's much more. I sometimes say CFD software is not a calculator, right? It's a tool which helps the engineers to make their projects successful. But software is, at the end of the day, it's just 40% of success. The rest is the focus, the skills and experience, and the dedication to the topic and to the project itself. And so if you ask me today what we are selling, it's definitely not just a software. It's a knowledge, and I would say it's the ability to make your project successful. And the part of it, a very important part, maybe the most important part of it is the knowledge. It's know-how, it's skills, how to do things properly. Because even if there would be something like the best software of them all, it would never make the job properly for you. It's always a mix of these skills, experience, knowledge, and the software and the deliverables, and also the topic, and every project is different. So it's extremely complex, but it's not just the software. That's point. Definitely my point at the moment. But yeah, we are showing all the stuff in the software. So, but it's that's how we do it. So TCAE is in fact a set of multiple software, I would say, modules, and each module consists of even more software components. So it's definitely a complex system, but the most important, I would say, settings is explained with the modules. So there are TCAE is a software of modules where you can use, for example, module for meshing, module for CFD simulations, FEA for acoustics or for optimization, or not at all. You can in fact you can pick the most important I would say principle we follow is that TCAE is extremely flexible, so you can use it together with other open source or with commercial codes or with in-house codes. The principle is always the same. You can pick only those modules you would like to, and use pretty strong interfaces to join or to merge or connect to another software and create your workflow that fits your purpose, that fits your goals and experience and the resources and everything. So that's very important principle. TCAE is extremely flexible, and we're definitely ready to prove it. It's unlimited, so there are no extra costs for additional users. There are no limitations on job scores, sessions, hardware installations. So TCAE definitely allows its users to scale their resources to the fullest. That's a very important principle, and people like it for this reason. Together with it, there's a wide range of licensing, how to use it. We are very flexible in it, and that's what we can do quite a lot. So feel free to ask about your personal solution, I would say. TCAE is focused. It's not a general purpose code at all. So it's focused on particular workflows. So especially it's been created for turbomachinery simulations and for external aerodynamics. These two are golden, I would say golden eggs of TCAE. So it's focused on these types of simulations. And because it's focused, it can be accurate, it can be automated, and it can be really focused and deliver the best possible value. So it's focused. and it's well automated. It can be scripted, it can be run in a loop, it can be run remotely, it can be used in multiple ways. And the beauty of it is that it's always the user who decides how deep to go to the rabbit hole or not at all. So TCAE for this reason can be used just as a black box, or the users can decide all the details, because it's also open source. So you can view the source, you can see the equations, you can see all the variables, you can see everything. So that means it's transparent and I would say highly sophisticated software because of this, because it can be used as a black box, but it's absolutely opposite. It's not a black box at all. It's open source. I mean, the methods are open source, and algorithms and everything. Okay, so I'll move a little bit forward. We've tested accuracy is extremely important part of all the simulations and all the simulation software, of course. So we've tested TCAE on multiple benchmarks. Some of them we are allowed to publish. So there are a lot of benchmarks we can show to prove it's accurate, it's consistent, it's extremely powerful. It can be run it can be run remotely. It has a unique client-server options, so you can, for example, run a client version of the software on your computer you are sitting at, and the server and core and simulation can be run, in fact, in this client-server mode. Remotely, or you can run it on just locally on laptop, or locally on desktop, or remotely on cluster, or remotely on cloud, from work, from home, in Linux, in Windows, in Linux. There are a lot of options in this, so we believe that it's very useful in this, I would say, modern world where you can pick a lot of configurations, and the options are almost endless. As mentioned, the TCAE is based on open source code, so there are definitely more than 60 nowadays, even more open source projects in it. Its CFD is based on OpenFOAM, and FEA is based on Calculix, and there's a ParaView as graphical interface, and a lot of other very useful and important open source projects are included, and we mastered the ability to put them together, teach them how to communicate each other, and put everything in a smooth single package which is ready for professional use in the industry. That's very important. Those open source are great, they have great potential, but when they definitely need to be put together to deliver the value for especially for the industry, because everything has to work perfectly. So we've spent additionally on top of these open sources, we have spent more than 40 many years in aggregation, of course, with development of this consistent workflow, graphical interface, and everything to put everything together, and that it's a value itself. And perhaps another value is that it allows you to keep the software, have it permanently on your local computer, and keep your knowledge under the roof without, I would say, exposing it to a danger of intellectual property issues, etc., etc. So it allows you to work on your computer and produce the value you would like to. So it's extremely important part, and that's what our users like about it. Okay, so now it's version we are using the version 24.3. Of course, we are developing the new version. Again, the new version likely will be version 24.10, which will be released sometime after during the summer or early in autumn, September, October, perhaps. And there will be again new features, new updates, and new capabilities. And for the future, we will definitely focus on the optimization, on improving the acoustics and really have this vertical as strong as possible, the acoustics, and yeah, creating databases and surrogate models. That's our great future plan, and we are working on it, and we are looking forward to show it to you later this year or next year. Okay, so it means that we have yeah, that's the general part, and now I would like to invite the expert to this presentation, and I would like to ask Dr. Maca if he is there, so he can hear us. Yes.
Yes, I'm still here and ready for my part. Yeah.
That's great. That's perfect. So Radek, you can go ahead. I will switch. Yeah, that's what I have to do. I will switch the presentation over to you. Yes, we can see your screen, so you can go ahead. The stage is yours.
Okay, thank you, Luboš. So just to mention, do not hesitate to interrupt me anytime if you find that something is important to say in the middle of my speech. Just say it. Yeah. So let's go in this way. So just to introduce the real or the part of presenting the specific workflow in TCAE, we will split this part into the, let's say, 3 sections. So first section, what I would like to show you is how to prepare the inputs for TCAE, because it's really important, and we typically directly start with the STLs, but I would like to try to show you and to present how the STLs should look like, and how to create the inputs for the meshing. The next part will be how to set the mesh parameters and create a computational fluid domain or computational domain, and the last part will be how to set the CFD setup or FEA setup if you will still have time to present it, and maybe finally we can talk about the results and visualization and so on. So let's go directly into it. So today we will be speaking about the centrifugal fan case. So for your reference, you can go to our web pages, click on case study sections, and here under the centrifugal fan icon, you can go to the page for centrifugal fan just to read more information about this case, download the case, and try, for example, by your own on your site. So to present the first part, I will borrow in the documentation the TCAE training part, and somewhere on the slide 31 there is a introduction of how what are the requirements for the input for the meshing, because it's the main part of your workflow, or where you should start creating the workflow, is to have the CAD geometry. And from the CAD geometry, you need to create a proper input for the meshing. So I think this is pretty clear. So you need to extract the flow domain, we call it wet surface, from your complex geometry shape. And this is the first part, to create the flow domain. So this I think is pretty clear. The second option is to tailor the flow domain, and then afterwards exporting the STLs towards the proper requirements and inputs, which then leads to a nice setup for the CFD simulation. So here, because we are speaking about the rotation geometries, we need to split the flow domain into the components, we call it, and the components can be distinguished as the rotating one and a stationary one. So the splitting has to be done typically in the CAD by creating another surfaces, which is called interfaces, which defines the interface between stationary and rotating part, or in general between two adjacent components. So when creating the inputs for the meshing, we need to we need to keep in mind that we need to create some additional surfaces which will define the interfaces between the typical rotating and stationary parts. And the second way of thinking is that we need to split the domain to properly assign physical boundaries and afterwards boundary conditions in the CFD setup. So we need to separately extract the parts which create the inlets, which create or which defines the rotating part, stationary part, or for more complex analysis, for example, you would like to focus on a particular part in your geometry to evaluate, for example, forces. So that part on which you require some specific evaluation, you need to also export it individually as an individual part, because afterwards you would like to set some advanced evaluation on it, for example. So this is all the necessary features which must be followed to have a nice input for the meshing and afterwards for CFD setup. So I think for now this would be enough, and I would like to go directly into the real example. So today I try to be brave and directly start just from the CAD geometry. So for example, on our side we use Salome, which is also open source CAD software and we use it for modification of the CAD and for tailoring it and tailoring it to TCAE needs and for exporting STLs for the meshing. So I will open I will load our CAD model for today. So import, I think the step geometry file, and I will go to our working directory, which is somewhere here in the webinar, Centrifugal Fan, and here I have the CAD model. So this is the exported model for the Centrifugal Fan, and it already defines our flow domain. So typically this you need to do in your complex model just to extract the flow part. And what is also another thing is to clean it and clear it from any unnecessary parts or very tiny shape which does not influence the overall efficiency or the targeted parameters you would like to follow. So the best results you always achieve with a nice clean geometry. So as you can see, the geometry includes all the parts we would like to model. It's a simplified geometry without any shaft or shaft geometries and all other details. And for example, here what we need to add at the first time is to create the interfaces, because this is the simple model which is not ready for the CFD simulations. So first we would like to create the interfaces, so some kind of surfaces which cut off the rotating part, and using them we will be able to set the interfaces. The next part will be to split the domain into given STLs, given parts, which then will define the the mesh model, basically the geometrical model, and afterwards these parts which we will create will be used to create boundary conditions and splitting of the domain in general. Okay, so I will quickly try to create the interfaces. So first let me do the splitting of the model. So typically we can some kind of explode it into some kind of geometrical parts. It depends on the export from your CAD model or whatever, or if you do it directly in your CAD model, so you know how to treat it. So for example, I would like to split my model into several shells, and as you can see, includes some kind of inlets and outlets. Then it includes the volute surface, some kind of suction wall, and the impeller inlet, or solid of the impeller. So first, how to create a rotational domain. So typically we need to create or define the domain which includes all the all the rotating parts, or at least all rotating parts which are not rotational symmetrical, or how to say, which do not have the symmetry, because all these parts, all these rotating parts has to be included into the rotating part to properly treating all the rotating effects within the simulation model. Right, so first I will create the inlet interface. So in this geometry we can create the inlet interface directly at the edge on the impeller. So to do so, here I can, for example, create I can take or extract the edge here on this side of the impeller. Okay, so I will do it, and now based on the edge, on this edge, I can create a face. So here I can click build the face, and now I have new surface which will split the inlet suction and the rotor part. So this will create the first interface. Now I need to create the outlet interface from the impeller. So the general rule of thumb is to create the rotational domain as small as possible, because then inside the domain specific physics is applied by some rotational framework, and it is the most robust and the best way is to do this domain as small as possible. So one option would be to create, for example, the cutoff by cylinder somewhere with the contour above the edge of the outlet of the impeller, and do the large domain. Or the second options is to just include the rotating part just in the flow channel of the impeller, and because of the meshing purposes, because we need to mesh everything, and the mesh needs to have some kind of space to create, for example, small meshing at the edge of at the trailing edge of the rotor and within the impeller area. So let me do the second option. So to create some kind of edge here and rotating object to create some kind of interface at the outlet of the impeller itself. So what can I do here? I can create some kind of leading points at the outlet from the impeller. So for example, I set the new coordinates. So I will do some kind of extension to have space for the meshing at the edges. So because if I do it too close to the edge, then the mesh refinement should be really fine, and this is not necessary. So I can do the extension and on the both sides, and then I can create the lines which I will rotate to create nice interface as an outlet from the rotor, from the impeller. So now I can create a rotation. So new entity generation and revolution. Nice. So here I will set the axis. Axis of rotation is the y-axis, and I would like to rotate it by the 360 degrees to create a full interface for the full wheel geometry. All right, so this is the one option. I think the most suggested one to do. And now we have defined a domain for the impeller itself, and which divide the inlet suction part and the volute part from the rotor. What can, as an example, what can I show you? because CFD likes the extended outlets typically, because the boundary condition works the best at the part where the flow is steady, homogeneous, no big recirculation are happening there. So sometimes it's nice or clever to define the extensions of the volute. So just let me visualize the volute. And because I have this shape separately, so I can do the extension, for example, as an example. So I can do the generation again, now the extrusion. Now it follows the x-axis. Okay, and I would like to do, for example, extension of 5 meters. I think this will be really enough to give the flow space to come down and to be steady at the outlet, because then the boundary condition is most robust one, and also from the view of the simulation, it's more stable than if you put the outlet interface somewhere, or outlet itself somewhere where the flow is too wild, too many recirculations are happening there, because the accuracy goes down. Also with prescription or the, for example, ambient condition or some pressure drop, it's better to preset it somewhere where the flow is calm. Okay, so now, so we have created the interfaces, we have created the extension. So now the main part is to create the STLs and create separate parts of the geometry. So first of all, I will create the model, which includes all the geometries. So just I will go rid of everything, and I will calmly set. So this is the volute. Okay, let me go back. So this we have the volute. Then we need to add, of course, the inlet. Then we have the suction wall, let's say, the suction part. Then we will add the interface here. We will add the impeller itself, the outlet interface we made, and I think the last one is the extrusion, because also it includes the interface. So we can set this extension as a separate part, because then we can set the evaluation, for example, directly here at this interface for efficiency evaluation or pressure drop, because, for example, we have some kind of measurements here at these positions. So we would like to keep the interface here to have integral values of all the quantities available at this position. Right, so now I will create the one shape, kind of compound for all parts, and I can call it centrifugal fan. So all. Okay, so now we have one object which defines all the parts we need for the meshing, for creating the flow domain model. Okay, so this is all. This is kind of cleaning and creating the interfaces, and now we need to create the parts and export them as the STLs. So the best way to create the STL is to create a triangulation for the object as a whole, because then we will have the point-to-point correspondence. The triangulation is done for the whole model, so we will be sure that there are no holes, no areas which are not, let's say, which doesn't fit precisely. What I mean, if I go back to my presentation, for example, this is typical when you're exporting the parts separately. So then it may happen that there are some holes in it, and this may then trouble for the meshing, or it can create some kind of flaws in the resulting mesh. So the best way is to triangulate the model as a whole. Okay, And to have the separate parts, so for example, here we can create a groups on this model, and these groups can be then exported separately. So let me quickly create these groups. So for example, this will create as a group, including this face, which is the inlet. So I can name it as inlet. Then I can, okay, I will hide this. Then I will create this suction wall. So all these three parts I will add to the new group. Okay, perfect. And I can name it as suction, for example. All right, then I can create a volute part. So let me click all the parts of the volute. So in this way, you can nicely create the group. Okay, so for example, volute. Let me hide what I have selected. If okay, that was all perfect. And this you can do for all the parts, because I don't want to bother you with these just clicking and setting up these groups. So as an example is okay, because in advance I have exported it and create all the parts for our next step of setting the mesh parameters. And then here there is a module for discretization, for meshing, for example, the 2D surfaces. So I can click here, I can create the triangulation by the netgen typically. Here you can set the meshing parameters, so the sizing of the triangles. So let me set some rough estimate for the for the sizing. So 1 millimeter as a minimum, for example. Now we can apply this, and I can run the triangulation just to show you how it works. So I hope I set everything perfectly. So now it creates a triangulation on my surface, and because I have created the groups on the object, I can then export the groups as individual parts. So now I can go, for example, volute, export STL, and for example, save it here. And then in this directory with cat, I have first part, which creates me the volute part. Yeah, and similarly, I can do for all the parts. So if I do all the groups generation and exporting to STLs, so I have created in advance here cat geometry, and I have here all the parts we will use for the setting the mesh parameters. I made it simple as possible, so I made just as few parts which I needed for correct definition of the flow domain and for correct definition of the mesh itself, because then for final tuning you can export separately, for example, pressure suction side, the trailing edges itself to impose high level of refinement and to play more with the mesh. But for the sake of simplicity today, I have created just as few parts as possible. And then all these parts, like for example, to volute together, and all the parts will be used to create and define the mesh parameters. So this is the most important part before you even go into the TCAE and start creating the flow domain and setting up the CFD simulation itself, or FEA simulation, or even more for optimization, because then you need to be expert in what you do to create a nice workflow. Okay, so the next step will be to go for the meshing. So maybe if Lubos has any note on this section, so feel free to take the presentation, or if not, I can smoothly continue
Yes. No,
into the meshing
Radek,
part.
yes, absolutely. As we agreed in the beginning, before today's webinar, we just spontaneously agreed that I could comment, make some comments in specific points in the presentation, which I did. I followed carefully, and I hope you can see my screen. I changed the presentation a little bit, and I think I can comment a little bit, because I think it's important to make a little summary here.
Okay, we can see it. Yeah,
So
we can see it.
okay, that's great. So yeah, so hopefully it's there. I just spontaneously write this down a minute ago. Actually, it's in the middle of editing at the moment, but still, I'll do my best. So a little summary on workflow inputs. When you want to run the simulation, your first goal or your final goal in creating these inputs is creating the volume mesh, right? Because those solvers are based on a finite volume method, so you need the volume mesh, which is I would say it consists of cubes in the space, and you need to create it, the volume mesh. I hope it's clear what it means. And when you do the simulation in TCAE, you have two options. You can either import the ready-made external mesh externally, which has been created in another software. So some of our users do it because they have some existing workflow already. So you can load the mesh in MSH format, CGNS, or in OpenFOAM format. So that's you just load it and skip the rest, and you do not need to care about the rest of the workflow. Or you will use the T-Mesh, which is the meshing tool, which is semi-automated tool, which creates the mesh for you. It can be extremely complex, but it still works, because T-Mesh is based on SnappyHex mesh, which can mesh almost anything for CFD simulation. So that's what most of our users use this option. So the automated meshing. So this is what Radek has just described. You need to get the simulation ready geometry, and that means that in some CAD system we use Salome, but we do not push it too much. It's a little bit, I would say, specific. We use it because it's free, it's open source, and we can gladly recommend it to anyone who wants to deal with it and do not want to spend an extra costs on additional CAD software. But you can use any other CAD system. The principle is always the same. What you are going to do is you split your model into several components, because it's for good reasons, because some components are rotating, right? So we need to split them to allow them to rotate, and some components are static. But the basic principle is you are going to split your model in components. So it can be, for example, in our case today, it's the centrifugal fan. So it can be, for example, component number one can be the inlet tube, the suction tube, basically. Then it can be impeller, for example, which is rotating. So we technically make its own mesh for it, because we want to be able to allow it to rotate. Even if we use static methods, it's smart to have this option to let it rotate. And then it can be, for example, the spiral and the outlet tube. So you can have any number of components. But what is important is to this component thinking, right? So you split your model into components. Another important point is the components should be created to be as simple as possible, and definitely they should be watertight. So if you pour the water in it, it should be resistant. It should stay in it. So they should be watertight. Sometimes we say waterproof. It's a surfaces, but closed surfaces. I hope this is clear. And what else have I here is, so for each component, you technically create STL surfaces, right? Those are just surfaces in space, which close the components perfectly, and or as much as possible, but ideally perfectly closed. And they have either interfaces, so we call interfaces those like virtual surfaces, like inlet, outlet, and interfaces between components, and walls. the walls are rigid walls like or the general walls, or of course blades and hubs and shroud, or those rigid walls. But as that's the meaning of wall. It can be anything which is solid, solid part. And interfaces, they don't really exist. They only act like imaginary surfaces, because we want to have we want to be able to prescribe the boundary conditions and know the flows through them, and etc. etc. Yes, so this is the way how you do that. This is what you want to achieve, to be able to create your volume mesh with T-mesh. And there are perhaps a couple of points I wanted to mention, which I didn't. And at the end, I want to always to say, it may look complicated, but definitely it's not. It's something, for those who see it first time, it looks like complicated, but everything is about practice, experience, and training. And by the way, almost anything can be automated. So don't worry, you do not need to do all this all the time. If you make it in a proper way, anything can be scripted, automated, and you just can have everything get automated. So don't worry about that. We are here to help, and we did it 100 times in the past, and so don't worry about that. So those are the inputs, and it's important to understand what you put in. And by the way, these inputs are the most I would say it's the bottleneck of all workflow. If you know how to do your surfaces, the rest is much more simpler. It's not difficult to set up the simulation, it's not difficult to run the simulation, it's not difficult to process the simulation and view the results, etc. Everything, but the creating the geometry properly in the beginning, we call them inputs. Basically it's the geometry. So to create the geometry properly is typical a bottleneck, because it's very sensitive. If you do mistakes in the beginning, then it cannot be cured. It cannot be helped later, right, during the simulation setup or in post processing. So you in a way you determine your ambitions on the results in here in this phase when you prepare the geometry. That's my those are my notes. That's my little summary about this first part. We have quite a lot of materials on our website. There's a quite extensive presentation for the training. There's also the manual, which is quite extensive, and there's also our technical support. So don't worry about the complexity. We are here to help, and there are a lot of materials for that. And that's from me, Radek. If you like.
Outstanding. Thank you. Perfect. So I think I can nicely go for the meshing part. Yes. And let's directly open finally TCAE. So mainly I would like to show you how to create mainly the topology of the mesh, and maybe then we will set some kind of quick setup for the parameters for the meshing. But the main part in my demonstration will be how to create the components and how to create the topology itself. Okay, so I just opened the TCAE and directly click the T-mesh, but first I need to create the new project. Okay, so I may make it full screen. Now I create empty project. I will save it into my working directory. So let's go to the webinars, today's webinar, and TCAE project, or TCAE Fan, for example. Okay, so I will save it here. And now first I will activate the module T-mesh for the mesh generation, or even for the mesh processing in general. So even you have the external mesh, you need to activate the T-mesh and load the external mesh, etc. But today we will go for setting up the mesh using the STLs. So first of all, in the general section, it's pretty straightforward. the mesh output will be now just for the CFD mesh, but you can also create the mesh for the FEA analysis. Maybe later we will go there, or maybe we will mention in more details in the next webinars. Scale factor means the scaling factor, because everything has to be scaled to meters, to the SI units. So if your input geometry is in millimeters, it must be said here that the inputs here is in millimeters. So I will keep in meters because my STS was exported in meters units. Any section in general has some kind of scripting, which Luboš already mentioned, that it is nicely scriptable and can be tailored to your particular workflows, or can be connected with some external tools, external scripts, and whatever. So this is kind of user-defined scripts to tailor the solution to your needs. But now let's go for the CFD mesh. First, here in the rotation reference frame, these are used for the setting properly the rotation itself, and for setting additional geometrical properties of the interfaces, typically referred to the axis of rotation. So maybe I will keep this, and then we will back when we load the geometry, then we will see what is our axis of rotation. Now we are going to the components, and here we need to define as many components as we need. So in our case, we will have 4 components. So I will set to 4. We will have the inlet section or inlet tube, the impeller region, volute region, and the extension region or extension component. So let's start with the first component. So first item is to load the input geometry. So we have 2 options: either load the geometry surfaces, which is our case, or import volumetric mesh, which can be the other option. So now we have the STL geometries. So I have here in the kit geometry, and now I will import basically the parts which will define the component 1, the inlet suction. So we have the inlet here, we have the suction, and then we have the interface which we have created, and I name it as interface rotor in. So whenever I load it, it will appear in my render view, and we can see all these parts. And if you double click the item here, it is also visualized in the render view. Then you can clear the visualization by this icon of a trash here. All right, now we can see, because it's the inlet into the impeller, we can see that our axis of rotation, or our reference frame axis, are in the wrong position. So we will adjust them to the y coordinate, or following the y-axis, and the same I will do of course for the rotating regions. All right, then I can go back, so I can continue with the setting up of the mesh for the component 1. Here, component name, I can define my own name for this region, so suction or inlet, whatever you like. Reference frame, because it's not rotating, it will remain static. We don't have any periodic geometry. This is for geometric, for segment geometry, where you do not simulate the full wheel geometry, but just the section. Typically for axial machine, you have just one blade section to define the flow domain, and you simulate it as a periodic geometry. But this is not our case today. Then we have these 3 items to define this this part. So first I will assign just the properties and not the mesh refinement itself. So the type of the boundaries are, I think it's pretty clear. If you would like to enable some kind of specific turbomachinery parameters, you can click this option, and then we have more items here, which are mainly for turbomachinery purposes. And for example, we are more tailored names for defining the blade, hub, shroud, etc. for easier reference later, for example, during the mesh visualization or processing of each part of the flow domain. So here, the inlet, for the physical inlet into the domain, we have the inlet type. For the interface, we have several types, like inlet interface for flowing in, outlet interface for the flow out of the domain or of the component, and the free stream interface for some general interface where we do not know or we don't need to set the proper flow direction on that specific part. So we have here this interface, the outlet, because the flow goes out from the component, and this is okay. Let's continue with this kind of settings for all the components, just to create a whole model, and then we will continue with setting of the meshing parameters. So component 2 will be the impeller. So I can call it impeller or rotor, whatever. Now the reference frame should be rotating, because now we would like to prescribe a physical rotating or the rotation from the physical point of view. And now again, I need to load the geometry. So here we have again the interface rotor in, interface rotor out, and the impeller itself. So here we have it. And again, continue with the settings. So impeller, we can set it as a blade, for example, or whatever, or just simple wall, because we have everything shrink into one object. But typically we can split this impeller into the hub, shroud, edges, suction side of the blades, etc. Then we have the interfaces. So interface rotor in is the inlet interface, and interface rotor out is the outlet interface. And because already we have the inlet component or one component connecting to the impeller at the inlet interface, we can directly connect the component to the inlet part. So if I right click the inlet interface, and I know we would like to connect it to the suction, and we have only one option, because we have only one interface on the suction side. So we will click interface rotor in. Now it is connected. To check the connection, we have here the section components map, and it will show you some kind of topological graph of the flow direction for each component. Okay, so outlet interface not already set, so let's go for the component 3. So it will be the volute. Volute is again the static part, and let me load the surfaces. So here the inlet will be into the volute part will be the rotor outlet. The outlet from the volute I have named or exported as interfaced volute out. Then the boundary of the volute is the volute, volute STL, and because we have the impeller, which create the whole solid of the impeller, and this part also create the volute part, the outside part of the impeller, we need to include it also into the volute part. And we can do this because the outside part of the impeller is symmetrical, so we can then impose some kind of rotating boundary conditions, so rotating velocity like boundary conditions to mimic the rotation of the solid of the impeller inside the volute part. Okay, just to see inside, you can go click on the CFD geometry, go to the display section or display menu, and decrease the opacity value here, just to see what is inside. And what I also like is to create some kind of meridional slice. So you can create a slice, and which goes to the origin, because the axis goes through the origin. And now you can see some kind of meridional slice. And nicely, if you go to the multiple inspector, you can see which parts creates the boundaries of the impeller of the volute itself. So the outside part you can see will be also defined by the impeller. Then we have the rotor outlet. Volute interface is not here because it's not on the slice, and the volute itself. And this show me that I forgot to include also this suction side, because it also creates the flow boundary for the volute. So I need to go back and re-import these components. So sorry, to the T-mesh, back to the components, to the third part, and I need to re-import the surfaces and add also the suction wall. So again, I need to click the impeller interface, rotor out volute, volute interface, sorry, volute, and the suction. Okay, now I will reload it. And if I go here just to check the slice and the contours of it. So now you can see we have the impeller interface outlet. This is not visible, volute, and the suction side, suction wall, which also creates a part of the flow domain. All right, so this we have. Now we need to assign the proper boundary conditions, boundary types, sorry. So impeller, again, we can set it as what we have to be. Okay, we have a single wall, so I will set it as wall again. Interface rotor outlet is now the inlet into the volute part, so I will set it as inlet interface. Interface to volute out is the outlet interface. Again, I can already connect it to the impeller. So now I made a connection from the impeller to the volute. Volute, we can set it as wall. Suction, we can set it as wall. And most importantly, because the impeller wall is rotating, we need to set this reference rotating frame as rotating. And internally, for the simulation, the boundary, it will be set the proper boundary conditions as rotating wall boundary type. All right. And the last one, the last component is the just outlet, for example. We will import the surfaces. So again, interface volute outlet, outlet, and outlet wall. Now it's loaded, and if I visualize back the 3D geometry, so we can see that we have now the full geometry loaded into the T-mesh. So let's finish the setup. So reference frame, we have static. Interface is now the inlet interface into the domain. So now I can connect it with the impeller, with the rotor out. Not with the rotor out, sorry, with the volute, with the interface volute out. Outlet is of the type outlet, which is used for the physical outlet out of the domain, and outlet wall is a rigid wall, so we can keep in this way. So now we can check the topological graph, and we can see that we have nice path from the inlet to the outlet through all our components, and the solid line shows us a proper connection. So this is a good check if we do a correct topological connection for all the components. All right, so this is the topological connection and the setting of proper type of the boundaries, and then the rest part is to set the mesh parameters. So maybe just as an example, I will show you how to do that. So first one, the SnapX mesh started from initial state, which is made by a typical hexahedral shape with a uniform splitting of the cells. We have two options. So typically we would like to have the cube cells as the initial cell sizing. So I don't know, I will set, for example, 4 centimeters. And if you click the show background mesh wireframe, it will show you a topology of the background mesh from which the meshing will be done. So this is the largest cell or cell with a level of refinement 0. And then based on the boundary which intersects the background mesh, you can set the refinement. So for example, I don't need any refinement on the inlet, but I would like to have, for example, refinement on the wall, and to do the proper mapping or connection of the interfaces, I would like to also refine the interface interface patch to level 1. Then what you need to set is internal point to properly define the parts of the mesh which will be keep for the meshing, or basically for the simulation. So you need to place the point inside the given component. So you can use this interactive feature to visualize the internal point and move it into the component, or you can set the values manually. And this basically must be done for each component. So I don't want to bother you with the settings. A typical this must be done for each component, and to have the final mesh is a matter of several iteration and experience. And maybe I have one slide in the training. So for the good meshing, and maybe Lubos can also join me in this place, because then I will jump directly to the mesh which is already set up, and then we will go for the CFD simulation. So what is necessary to have is a perfect STLs, as we mentioned in the first part, and then you should start from rough meshes. So you don't try for the first attempt to have a perfect fine mesh which is the best and final mesh you can have. So start with the rough meshing, because the mesh generation is fast, and you will see very quickly any topological problems or any problems with input STLs or with the topology you set itself, if you don't miss some part of the component or whatever. And then if the rough mesh is created properly, it means it fills all the components you have defined, and as a whole it looks like your desired simulation domain. Then you can gradually go step by step to increase the refinement at the places you need to refine, some kind of sharp edges and complex shapes, etc. And whenever you are satisfied with the volumetric meshing, then you can enable adding the boundary layer, which should be the final state of the meshing procedure, and to add your desired boundary layer to follow what your physics or whatever you need to achieve with your simulation. And the best first check, even you think that everything is okay, always visualize the mesh and look at the boundaries for the resulting mesh. If everything is smooth, everything is meshed properly, look typically for some collapse edges or whatever, which will show you that something is wrong, or that, yeah. So check the mesh visually all the time, and of course be patient. All right. So Lubos, if you have any note, just jump in and
Radek, yes, thank you. I think I suggest you would continue with the settings of the workflow. I mean the TCFD settings, and then I will come with couple of remarks, but just notes, and yeah.
Yeah, perfect. Okay, great. So let me continue. So I will borrow one of the preset cases. So let me borrow this one. Yeah. So this is the same geometry, same topology, but already set for the meshing. And maybe I will do, yeah, okay. So just first let me load the project. And okay, and let me get rid of the TCFD module. So I will try to delete it because I would like to edit live. And let me check the mesh. Yeah, so for example, yeah, this is the same mesh, but already we have set the particular parameters of the mesh refinement, of the refinement on the impellers. So this is very simple rough mesh. we have played just with the background mesh, or I have played, and with the refinement on the surfaces. And this meshing, let me check if we can see the final meshes here. Yes, we can. So I can open new render view. I can go to, yeah, this is the component outlet, sorry. Now if I click here, CFD geometry, sorry, not CFD geometry, but CFD mesh. So this is the CFD mesh, pretty rough, as you can see. And but I would like to visualize the whole mesh for all of the components. So this is the last item here in the table, is the final mesh, which looks like this. So some kind of fine or rough mesh enough for the simulation, just to have this quick simulation. So this is how you can check it visually. Again, you can do any slices you need to look what is happening inside and how the mesh looks inside of your domain. Or if you click here onto the CFD mesh and go here to the multi-block inspector, you can visualize, for example, just an impeller, how the surface look like, how the mesh surface looks like. So where is it? Impeller wall. So this is the part of the impeller which belongs to the impeller region, right? And there is the let's say outside part of the impeller which belongs to the volute impeller, which is this one. Get rid of this visualization. So this is the whole basically solid meshed for the impeller boundaries for the CFD simulation. And again, you can do it with any kind of object which was set as a patch or as a part of the geometry in the T-mesh section. Okay, so after the several iterations, you get the nice mesh, and then you can go for setting the CFD simulation. So to do so, you can enable the TCFD module, and now you can go again step by step through each section of the menus and setting the CFD simulation. So I will go through the most important parameters which you need to set to have a successful CFD simulation. So for the general, we are, as Luboš mentioned, the solution is always focused and in this case tailored to the turbomachinery applications, and we have one family of application which are the fans. So let's follow the fan type. Then in the time management, here you set how many points you would like to evaluate. So typically you can create within a single simulation the whole performance map by setting up several points. So for example, points means several conditions under which you simulate the fan or your turbomachinery design. Typically here we would like to, or the typical application is to simulate the fan at different flow rates to really reveal the whole performance map. But in this case, I will just set one point, for example, best efficiency point, and just for the simplicity, and then we can visualize, simulate it runtime during our webinar. Then the fluid properties, standard properties of the fluid. So I will keep as the default. So the air at 20 degrees Celsius. Rotational reference frames. So here static is static and rotating is set as rotating. And you need to set the rotation speed. So we have 3000 RPMs. What you need to take care of is the direction of the rotation. So if I visualize the input geometry, and mainly I would like to see the blades. So here the direction of the rotation follows the right hand rule. So if your time follows the axis of rotation, which is y-axis, which goes now inside your monitors, and so then your crossed fingers shows the direction of the rotation. So now if you try it, so now it follows in this way. So this is the positive direction of the rotation, which is in the opposite way than we need, because the impeller should rotate in this direction. So we need to add the minus sign to follow the proper direction of the simulation of the rotation. In the multi-physics here, you can apply some additional physics, but I think we don't need it to do. This is not the focus on our webinar today. Turbulence, we keep it in default. Turbulence model K-ST, but you can choose your favorite one or the one which fits your simulation the best, your best experience, for example. Now, in the simulation section, here in the solver part, you can set number of processors you want. So for example, my computer has 10 processors. Numerical order, first or second, typically you can go for second if everything works perfectly, for the sake of simplicity, and I would like to have the results as fast as possible. So I will stick now with the first order scheme. Now in the runtime evaluate quantities, important part, because here you set all the values which you would like to and parameters of the evaluated, mainly integral quantities and other quantities which you can then visualize or process. So here you can ask for defining some advanced quantities like wall shear stress, pressure coefficient, and other quantities. You can ask for the average quantities, because typically the solver iterates over iteration, and every iteration is some kind of result of the current state. But for steady state simulation, you would like to see just the converged solution. So the converged solution is not necessarily the last iteration, because the solution can oscillate itself even for steady state simulations. So typically you would like to write the average quantities over the averaging window to have more stable solution. So you can ask, for example, to write the average pressure, average velocity, and other quantities you need. Efficiency probe is the main item for overall evaluation of your case. It evaluates efficiency, torques, pressure differences, etc. And all these quantities are evaluated based on inlet and outlet pressures and the patches which define the torque. So for example, here we set the inlet as an inlet patch. Outlet, for example, we don't need to evaluate the efficiency from the point of view of the pressure, for example, at the outlet. We would like to evaluate it at the outlet interface from the volute directly. We don't need to take into account the losses in this extension, so we can define the outlet patch and the torque patches, because we have two parts of the impeller, one in the rotating part and one in the volute part. So we would like to include all the rotating parts basically to evaluate torques. So all these items will be selected here. You can ask if all the quantities are flux weighted or area weighted. So this option is area weighted averaging. This one is flux weighted averaging. Because for some specific fan parameters is required the wheel diameter, so we will set the wheel diameter, which in this case is 1.11 meters. We can explicitly ask for evaluation of forces on specific parts, so you can choose any part, for example, on the well, here is not anything interesting, but for example, on the volute, overall forces, which doesn't make any sense here, but you can have some part which is important for you, and to know the forces on them is crucial, so you can include it here. Probes are some kind of point values somewhere within the domain. Convergence check to speed up the simulation process, because sometimes not so many iterations as you set here are required to reach the convergence. So you can, for example, ask or set the rules when to stop the simulation. So for example, I prefer to stop the simulation based on averaged efficiency. I like the absolute value, and for example, if the efficiency does not oscillate more than 0.1%, I would like to stop the simulation. Here in the control sections, here are some kind of under-relaxation factors. Everything you can keep in default. Just check for the minimum maximum pressures for your particular application, because we have radial fan or centrifugal fan, and because we are in incompressible mode, so we are speaking about the kinematic pressure. So I will set some kind of these values for the pressure. Many other parameters for linear solvers, we can skip it. And the main part are the boundary conditions. So here you have many options to set, for example, total pressure in the inlet, at the inlet, velocity-like condition at the inlet, some specific conditions for the inlet, like opening, which is typical tailored for some specific open domain cases. But here I think the typical example would be the volumetric flow rate, and I think this fan operates at 24 cubic meters per second. Then turbulent inlet quantities you can help by some formulas. For example, via the turbulence, you can set the turbulence quantities with respect to the turbulence intensity and hydraulic diameter. So I will keep 5% of turbulence intensity and hydraulic diameter. I think the inlet pipe diameter is 0.7 meters. And the reference velocity, I'm not sure here, so I will set something like 5 meters per second. It's just for a rough estimate of the turbulent parameters at the inlet, which are not crucial. Just need to set the proper proper range, not a specific exact number. For the outlet, again, there are many options for setting boundary conditions, but here we will stick with the fixed pressure, even because we have the long prolongation, long extension, so we can set the fixed pressure as a constant value. If your outlet is somewhere close to some wild flow parameters or flow patterns, then you can go for the mean pressure, which just hold the constant value, but the distribution depends on the distribution of the flow at the domain. But it's not so stable like the classic fixed pressure, classic Dirichlet boundary condition. And the reference pressure will be 0 because we are in the incompressible mode. Similarly, you can set the boundary condition for the walls, but the default one are the rigid walls, so no slip wall with the standard wall functions. Interface conditions here, we will stick with the AMI, so kind of frozen rotor-like, but typically for axial machines, you can, and typically for just the segment geometries, you can go for the mixing plane. But here AMI is choice number 1, and initial conditions, you can set some kind of initial guess, which is not so much important, just some meaningful values just to initialize the solution. So typically what I give some kind of magnitude of order of magnitude for the velocity, some meaningful, which goes along the inlet direction for the inlet. And the turbulent values can be initialized by our boundary conditions. And the final section to go through is the post-processing. So now you can tailor the report. So you can choose the section which you will see in the final report, your favorite quantities and units, and some kind of other advanced parameters or advanced tasks for the software, how to treat the results, how to store the results, in which format, etc. And also we can ask for some specific turbomachinery visualizations. So let's for example set this meridional view, can be helpful here. The mesh will be, the the second, the impler one, and we would like to see the total pressure distribution, for example, meridional averages for the rotor geometries. Okay, now I can save my setup, and let me check if I have set 10 solvers. Okay, 10 processors. So I will run the simulation. Okay, some problems are there. So if I click the check, so project contains some errors. Maximum pressure is smaller. All right.
I'm sorry. Yes, you just confused mix and max. It was just sign.
Okay, thank you.
Yeah.
Right, you follow my steps. That's great.
I did,
okay,
yes.
yeah, perfect. Yes, it's here and it's highlighted. So first minimum pressure and then maximum pressure. Perfect. So let me save it and go for the simulation. All right, so now I will be checking the simulation, and maybe what I can keep here is to create some kind of line chart views here to follow the residuals, for example, and other quantities. So here I can enable residuals, and in this window, for example, I can enable following the efficiency. So let's wait for the solver. So maybe Lubos, you can continue. I will be checking the simulation, and then we can go back for checking the results and
okay. Yeah, the time is running pretty quickly, so I'll do my best. So yes, I guess you can see my screen now.
Yes, we can.
Just again, I made just a couple of notes here. So there were inputs in the first part, and the second part is this TCAE setup. So I will just quickly mention that. Yeah, once you have a ready-made geometry, then things go easier. But still, you have to be there are some steps you have to make. The volume mesh, you very likely need to create all the meshing options. You technically you mesh each component, and then the meshes are automatically merged into one big mesh. So there's one big matrix of quantities, but you mesh each component separately. That's important. Once you have a full mesh, we definitely recommend to start with rough meshes, because you can refine them very easily anytime. And of course, as you know, fine meshes increase extremely the simulation time, and that's what you do not need to see in the beginning of the project, because you want to be quick. You have to take quick lessons. You have to really be quick in your simulations and later judgments, because no project ever is done that you create just one mesh, make simulations, and have results, and the results are perfect. This is how it does not work. You typically the workflow is iterative. So you create, I would say, some mesh. You easy mesh, make the simulation, look at the results, think about it, and then you can make improvements, and then you move forward with these iterations. It's typical for the new projects, right? I'm talking here about new projects. Of course, if your workflow is tested well, then you use it just as a tool very quickly, and everything is automated. So what we are showing here, I hope this is clear. What we are showing here is a new project approach, right? So we are having new geometry, playing with it, new setup, and everything is new. So that's what you need to do in the new project. You definitely, once you have the mesh, you have to think about the outputs. What are your outputs and what are your goals? Always the goals. What are your goals? That's important in every project extremely, because these goals and outputs, they define your agenda, they define your settings and everything. It's extremely important to know your goals. So what are your goals? What kind of outputs are you looking for? Is it just the efficiency, or is it even more? Is it some time development quantities? So it's important to know your outputs, and based on them, you should later decide what are your settings regarding the simulation points. Is it just one point, one set of fluid flow, speed, and boundary conditions? And what are the times? If the simulation is transient or steady state, if it's transient, how much of physical time you need to compute, etc., etc. So those are the basics. Then you definitely need to decide the physics and set the physics, the fluid properties. You need to decide the solver, typically compressible, incompressible. You need to resolve the turbulence properly. Then you definitely need to decide and set the boundary conditions. Boundary conditions are extremely important. Boundary conditions define all your workflow, and if they define all the case and everything, they are extremely critically important. So boundary conditions. Then you need to definitely decide how to visualize during the settings, during the setup. You already should know how you would like to, what are the outputs, how to preset the post processing, because a lot of things is happening during the simulation, and you cannot change it when it's done. Yeah, and again, it may look complicated, but we are talking about a new project, right? It's a new project what we are solving here, so it's not that complicated when you have done it before. You extremely improve your skills and knowledge with every new project, and almost everything can be automated, and there is a huge chance that your project will be repeatable, right? So because you do not do new research projects every day, right? So there's huge chance for repeatability, and typically what works and what's good, it stays in your workflow for the future projects. So the repeatability is a huge benefit of all the of the workflow and this experience. Yeah, those are just quick comments for this part, Radek.
Yeah, perfect. So I don't know how many time we can. So maybe I can just show the results, and then we can go for the question and answers section.
Yes, Radek. Yeah, do what you can. Take it easy. Show what you have in mind, and we will move to the Q&A session. I would once again I would like to remind the audience to ask your questions. We will answer them, and as usual, we can of course answer them via email later if you like. Okay.
Nice. Okay, so after the simulation is done, you can go for checking the report, which is the main output of your simulation, and also you can visualize the results. So let me go quickly through the HTML report, which is the output, the main output of every TCAE project. So here we have I borrowed the FEA, so I jumped forward too much. So here we have the TCFD report, yeah, and the part of the report are several sections. First one is about the simulation statistics, some overall information about the project, the overall information about the convergence procedure via the flow rate and residuals graphs. And then you can go section by section. For example, for fun, we have the fun characteristic numbers like flow number and compression number. Because we have just one simulating point, we can see one point here for our best efficiency point for example. Then we can see the efficiency, torque, other forces, power, etc. And maybe just to show you how complex the report could be, is that we can take, for example, the example on our web page where several points are there. So let's wait for it. And meanwhile, so this is the report. Then I will show you some kind of complex report, and to visualize the results, you can go here, click the CFD results, and if you hit apply, then you can visualize all the quantities which were evaluated on your flow domain, and you can play with them as you want. So you can apply any filter which is available here. You can some kind of layer the filters. So you can combine anything which is allowed here or which is offered. For example, you can also do some kind of streamlines visualizations. So let me go, for example, with this point cloud. I will put it somewhere into the middle of our domain. So we can, for example, combine the slices here with the streamlines evaluation. You can play with the parameters of the streamlines, just to visualize as many streamlines as you want. You can ask from which field it is evaluated, for example, relative velocity inside the impeller and absolute velocity outside. You can play with the visualization of the streamlines itself. So you can make some kind of plastic streamlines. You can assign or color it by any quantity you want. You can play with the opacity. So we can enable opacity mapping for surfaces, which make it also more fancy, the visualization. So this can be done really in a straightforward way, and a wide spectrum of visualizations can be done. And maybe if I go back to the case and to the report for a complex more complex analysis, maybe the connection speed is not so well, but basically you can see such a report on our web pages to go through and list all the sections and available quantities. So we can look for the velocity magnitudes, mainly circumferential values, and many others sections are available for more complex simulations. Okay, so I think to have some time for the question and answers, so I suggest to stop it here and continue with the question. So this is our main task, what I would like to say.
Yes, Radek, thank you very much. It was very informational and really great. I liked it. Yes, so this is, we were a little bit long, so we didn't say everything what we wanted to say, but anyway, time is running very quickly, so I would like to ask the audience to ask your questions. I haven't seen many questions, and also some people already left because we were really a little bit longer than we expected. So yep, so ask your questions. We will do our best to answer them. And because I cannot see many questions yet, so I will allow myself to say a few comments, and then we will go back to see if there are any questions. So yeah. So anyway, there are quite a lot of I would say tutorials and examples on our website. I would definitely like to recommend you to visit our website, because all the case studies are downloadable. They are based on real projects we did in the past with our clients. Of course, we have marked those details that could disclose anything sensitive about the projects. So these are like real cases, but they have been made anonymous, I would say. So all of them are downloadable. And also this centrifugal fan, which we dealt with today into this webinar, it's relatively in detail described on our website, and you can visit the website and you can take a look about all the details, what exactly could be done, and we didn't say it in this webinar. So feel free to visit the website and have a look. The case is freely downloadable, and of course, as all our tutorials, it's easily repeatable, and you can make sure it really works and it does what we say it does. And definitely it's available for your confirmation, and double check everything, and feel free to take a look at it. Another important source for all these is the manual, which you can find on our website as well. It's like 300 pages PDF where you can see even more details if you like about all the settings, all the equations and everything, which is not clearly or directly visible from the graphical interface or from our webinars, etc., etc. There's also a pretty extensive training presentation where you can what we use for the training purposes. It also can show in a different way what we said here before. And the last source of information is, of course, our technical support, which is pretty extensive. And as you know, or as our clients know well, we never leave behind anyone, and we always help with everything as much as we can and as is possible. So feel free to get in touch with us directly, and we'll be definitely ready to help. And I'll go back to the questions if there are some, and let's take a look. Bistrik, hello. Yes. Is asking about if there is a tutorial on scripting of the workflow. I think scripting is in every case it's extremely custom. It's extremely detailed and specific for each particular case, and we haven't anything such as scripting tutorial, but many tutorials has some scripts, but it's kind of hidden in them. So I would recommend, regarding scripting things, I would recommend to directly contact our technical support, contact us directly, and we will need to we have to discuss it individually, because this is difficult to answer. Yes, and Prakash is asking whether there will be a video recording. Yes, of course there will be a video recording. I think there's an automated email which comes to every participant and also those unattendees, and it will be also on our YouTube channel. Yeah, there's YouTube channel where it will be uploaded soon, I guess tomorrow. Well, and because the time is running very quickly, I can see that there is no relevant question which is really practical to answer in the webinar. So maybe we will I guess conclude and finish. Radek, are you still with us?
Yes, I am.
I think it's time to conclude. So
yes.
Yep. So okay, I'll do it for all of us. So thank you everyone for coming. It's for us, it's a pleasure, and it's our job, and we like if you ask and we answer, and if we can help, it's our greatest pleasure. So thank you for your time. Stay in touch with us, and see you perhaps next time. Thank you. Bye bye.
Bye bye. Thank you.
Thank you. Bye bye.